In this video, we're going to be implementing the find or lookup function or method of a binary search tree. We're going to do it in Java. And if you remember, what was really particular about a binary search tree was its usefulness in storing data. And this was because looking up or finding a particular node or key in that tree was really fast and simple. And this was because of the ordering that it placed on the elements within the tree. So there was this property in the binary search tree where every parent node was larger than its left child but smaller than its right child. And this property was really useful for us because it will allow us to basically implement this find function or method, which could find any element in the tree in time big O of log n. So let's see how we could implement that. And before we do that, let's just first define our tree. And to define our tree, we have to define a node. And to define a node, we're going to basically assign it a class. So we're going to say class node, and it will have three fields that are really important to us. First, there is the left node. This node will be public, so we could edit and read it without needing any getters or setters. Usually you would have getters and setters, but right now, just for simplicity's sake, we're going to make it public. And then we also have the right node, and it's going to have, of course, the key itself. So we're going to make it, in this case, public int, and we're going to call it a key or value, whatever you want. Then, of course, it's going to have a constructor which will populate these values. I'm just going to declare it here. So public node, and it's going to take, of course, a left node, a right node, and a value, so the key. And what it's going to do is just assign those past values to the field values. So it's going to use this operator. This left is equal to left, this right is equal to right, and this key is equal to key. So there we have it. This is the definition of our node. Now we could move on to implementing the find function. The find function could be implemented in two ways. There's a recursive way and there's a non-recursive way. So first let's implement the recursive way, which is the simplest way. We'll call our function, it's going to return a node because it's going to find the node that we're looking for and it's going to return it, and we'll call it find in BST. Now what are we going to pass it? We're going to pass it the root node of the BST tree, so we could traverse the entire tree, and we're also going to pass it the key that it needs to find within that tree, the key that we're after. So what is the first thing that's going to happen in our function? The first thing that's going to happen is we need to eliminate any possibility whereby we're being passed a root node which is null. So if we're being passed a null tree or an empty tree, we have to detect that and return that it was null. So how do we do that? So say if root is equal to null, what are we going to do? We just return root itself, which is null. So the user who called that function will realize that there's an issue and that the tree could have been empty. What's our next condition? The next condition would be that the root node contains the key that we're after. So the key that we're after right here would be contained in that root node. So let's check for that. So we say if root.key is equal to key, then what are we going to do? We're going to return that root. This is the root we're after. So essentially what this function is returning is the node in the tree that contains the key that we're after. And in this particular case, we would have found that the key is contained in the root node, so we'll return that. Now what if this is not the case? What if we found that there was a root and it's not null, but it does not contain our key? So what's the next thing that we do? Now we have to use the property of a tree to find our key. Now if our key is less than the key in the root, then what are we going to do? We're going to eliminate everything that's to the right, that's the right subtree, the right children, and we're going to look at the left of that tree. So here's what we're going to do. We're going to say if key is less than root dot key. So if our key is less than the key within the root, what are we going to do? We're going to return find in BST, and then we're going to pass it root dot left and key. So what are we doing here essentially? We're calling that function once more, but this time we're calling it using the left subtree. So we're eliminating everything to the right because we know our key is less than the root key. So we don't need to look at the right anymore. Now what if it was the opposite? Then you have an else statement right here, and you'd call the same thing, but so find in BST, but root right.